Okay, good evening, everyone. Thanks for coming. I'm going to be talking about learning topology. That's trying to learn the topology of your data. And the goal of this is that this is actually a surprisingly powerful way to do a lot of unsupervised learning. So the goal of this talk really is to inspire you to look into some of these sorts of methods more, because I think there's a lot of value and interest in these sorts of approaches. So it's going to be a bit of a whirlwind tour of some of topological data analysis techniques. There's a lot more than what I'm going to cover here, but this will sort of whip through the grand scheme of a variety of things and give you at least a flavor and some intuition for how and why these things work and how it might be useful for you. So the goal of this sort of approach is really to try and have some nice sound mathematical theory in the background. In this case, we're talking about topology and homotopy theory and fancy math sounding terms like that. But at the end of the day, we also really want powerful, useful, practical applications for machine learning practitioners out the other end. So to start, let's have a very quick primer on some of the relevant bits of topology for what I'm going to be talking about here. So the first thing is the notion of simplices. And really, these are abstract spaces. A zero simplex is just a point. A one simplex is two zero simplexes. And you can just actually have that as an abstract set of just the two of them and say this pair is joined together. A two simplex is three zero simplices, and you're just going to say, oh, they're all joined together. It's that simple. It's the convex hull of these points. The key is these are interpretable as topological objects, and at the same time, it's really, really simple, and you can just handle it all combinatorially. It's just a finite set of points. That's all you need. So this actually gets useful when you start to glue these simplices together. And you can glue a simplex together simply by having a face of the simplex touch another face of a different simplex by sharing some of those zero simplices. And if you glue them together, you get a thing called a simplicial complex. Now, the beauty of this is that a surprisingly broad swath of topological spaces can actually, at the end of the day, be represented in this way. So except for a few strange pathological cases of topological spaces, pretty much everything can be represented as this simplicial complex type approach. And this is a really simple combinatorial object that you can just deal with in a simple way without having to deal with complex issues of topology and continuous spaces and nasty things like that. So next we have a theorem, and this is a picture of a theorem. You don't really have to read or understand it. The point is that there is a nice theorem in the background here which is doing all the heavy lifting for us, and there's a nice mathematical proof for all of this. And what it really says is that given a suitably constructed simplicial complex, it can capture the relevant topology of all these different topological spaces. So in other words, given a topological space and a cover, an open cover of that topological space, which is essentially just a set of sets that happen to cover the whole space, we can build a simplicial complex from that in a very simplistic combinatorial way and capture the topology of that space. And this all goes through with strong underlying foundational math that says that this will work out. Okay, so let's look at an example to see that in action. So here are some points in 2D. There's sort of an underlying space you might imagine that these points were sampled from, looking like some sort of sine curve. And what we want to do is uncover that sort of topology structure there via this. So what we're going to do is we're going to build a cover of this by simply putting an open ball over each and every point. So now we have, in some sense, something resembling an open cover of the space. We've got a whole bunch of sets. They sort of cover the space. So there we go. And then to construct the simplicial complex from this, we're going to go through a very simple process. If two of these open sets overlap, I'm going to draw a one simplex between those 2 points. If three of these open sets intersect triply, then I'm going to draw a two simplex between the three of them. If four of them overlap, I'm going to draw a three simplex between all four, and so on. It's that simple. It's just a combinatorial step of how do these open sets overlap each other. The end result that you would get out would be something like this. So we've got the one simplices for the pairwise intersections, two simplices for the triple intersections, and so on. And what we have here is a simplicial complex that captures a lot of the topology of that structure we drew. It's not perfect, but we'll deal with that in a little bit. So next up, I want to introduce some language and ideas that underlie a lot of what we're doing. And these are fancy sounding words from category theory, but without getting into the detail, I'm going to try and give you an intuition of what these words are for, because this is how math manages to build nice, interesting structures here. So a functor is really, you can think of it as a function between different domains of discourse. So when a problem is too hard in one framing, you can potentially transfer it to a different way of thinking about the problem. That's something we all do naturally, but you can formalize that in terms of math and actually have a nice way to take a problem that's too hard here, transfer it over a different space where maybe it's easier to work with. So if you want an example of that sort of thing, we might think about those topological spaces, and we can take something that's a continuous topological space that's very complicated to deal with, and then we can translate that into a simplicial complex, which is now a nice finite combinatorial object that we can just compute on. So we can take something that's continuous and hard to deal with, translate it to a different domain of discourse where now it's finite and combinatorial and simple. And adjunction is essentially a near equivalence between two different domains of discourse. So it's an almost inverse pair of these functors. So we can sort of translate from one language to another language. We're not perfectly preserving the meaning, but we're getting about as good as we can get. It's a good enough translation, essentially. A limit in categories is essentially a way of solving a system of constraints. In a sense, it's the largest object that satisfies all the constraints of this system you're taking a limit of. And because in category theory things usually come in duals, there's a notion of a co-limit which goes the other way. And in a sense, this glues together a system of objects. So where one was finding the largest object that happened to satisfy all the constraints, this is the smallest object that satisfies any of the constraints, if you like. So this is all sounding very abstract. So what can we actually use this for? Can I actually motivate this with some practical examples? So let's talk about dimension reduction. The goal here is, in unsupervised learning terms, taking a large dimensional data set and trying to represent it in a smaller number of dimensions while capturing most of the fundamental underlying structure that the data had. So here was what we did in our first example with those simplicial complexes and the nerve theorem, and it wasn't quite working for us. And why was that? Well, in the end, it's the fact that if the data was uniformly distributed on our manifold, then we'd actually get a good cover. If we go back to way back here, I said this was a cover of the space, but if you sort of mentally draw in that sine wave, some of those open balls are not actually covering the whole space that the sine wave is sort of drawn on there. So we're not covering the whole thing. Whereas if the data was uniformly distributed, now when I draw these open balls, I'm actually covering that whole sine curve. So now I have an actual cover of the underlying topological space that I cared about, and now the nerve theorem, you can see, would give us the right thing. You can look at the pairwise intersections on that, and it's all going to work out very nicely. But when is real data that nicely behaved? Real data isn't nicely uniformly distributed in your space. So how can we work around that? Well, I'm a mathematician, so I just cheat and assume that it's going to be true. So I'm going to assume that the data is uniformly distributed on the manifold. The question one now needs to ask is, well, what does that tell me about the manifold? Because in practice, what it means is that the notion of distance on that manifold is not what I thought it was in the ambient space. It's something else, so that the data is uniformly distributed. And we can actually do a little bit of math and work out how to essentially vary the notion of distance across the manifold locally so that the data will be uniformly distributed. So a quick refresher on manifolds. Essentially, the goal of a manifold is to represent a complex, potentially curvy space by gluing together these little patches. Each patch can be mapped to a nice, simple Euclidean space, and wherever there are overlaps between these patches, we can sort of map between the different patches so we can smoothly vary as we go. So the key here is you can think of these different patches as being potentially on different distance scales, so that in one region of the space where the data is sparse, my distance scale is very spread out, whereas on a different patch of the space where my data is very dense, it's much more compact. So we can stretch or shrink our notion of distance according to the distribution of the data. And under that notion of distance, all of a sudden, magically, the data can become uniformly distributed. Okay, but another assumption is going to creep in here because we want to be able to apply the nerve theorem. And it turns out that I said there are those pathological, horrible spaces that simplicial complexes can't represent very well. Well, if the manifold isn't locally connected, which is just a topological assumption, then we're potentially going to end up in one of those messy, nasty topological spaces that I can't model with simplicial complexes. So I'm just going to declare that my manifold is locally connected. In practice, what that means is that no point is going to be isolated all by itself. It has to be connected to at least one other point. So if we put all of that together, we'd get a cover that would look something more like this. So we have complete confidence in our cover out to the first point, and it's going to scale according to the density of the data. So our distance scale, in some sense, each and every one of these points has a unit ball around it, but the size of a unit varies depending on the local density of data around that point. And as I get further and further away from that point, my confidence in how well I understand the metric space in that region is going to decline, so hence the fuzziness as we fade out. But I've swept a problem under the carpet here, which is that all these local metrics are incompatible with each other. So when I was talking about manifold theory and everything was nice, I had all these patches, and these patches might essentially have different metrics on them, different notions of distance. But down the bottom of this diagram, I have these maps that sort of map back and forth between wherever the patches overlap. That's what happens when you actually have a manifold. But I only have this finite data that I've sampled. So I don't have those maps. I don't know how to vary as I go from one region of the space to the other. All these different locally defined metric spaces are all just incompatible with each other. They don't know each other's notion of distance. So the way we would like to do this, if we were a category theoretician, is to just glue everything together with colimits. I said that's how you glue things together. That's the right way to do it. But colimits of metric spaces are rather hard to compute in that they don't actually even exist. So we need to somehow shift our problem somewhere else where we can work with it. So oddly enough, there's a nice adjunction between finite metric spaces and fuzzy simplicial sets, which are awfully like these simplicial complexes, but just a slight variation on it. And colimits there exist happily. So we can actually glue all these things together as long as we translate our problem to a different space. So we get something sort of like this out, where now I have just the one skeleton, just the one simplicity, zero simplices and one simplices, but each simplex has, in a sense, a probability of existing. It's fuzzy. That's what we got out of this adjunction. Rather than just getting a simplicial complex, we got this fuzzy simplicial complex where each simplex has this notion that it may or may not actually exist, and it has a degree of existence. So that looks like we've captured the topology of the data reasonably well with this essentially probabilistic graph. So suppose we had some low-dimensional representation. We could get a low-dimensional representation simply by scattering points randomly in a low-dimensional space and saying, okay, that'll be a low-dimensional representation to start with. But given such a thing, we can apply the same process, and we can get a probabilistic graph for that low-dimensional representation. And then, seeing as we're dealing with probabilities, we can ask about the cross-entropy between these two things. So I have a probabilistic graph for the low-dimensional layout I had. I have a probabilistic graph for the original source data. And I can say, how far apart are these in terms of cross-entropy? And then, seeing as I have a measure of how well the low-dimensional representation captures the high-dimensional data, I just optimize that. You can take gradients, stochastic gradient descent will do the job, and you effectively get a force-directed graph layout algorithm out of that, which will provide you with the low-dimensional representation that has this probabilistic graph structure most similar to the one that represented your original high-dimensional data. So, how does it work? Well, this term here is basically going to mean that we're going to get the clumps right. It's going to provide an attractive force which will pull things together if they were close together in the high-dimensional space. And then this term will push things apart in the low-dimensional space if they're far apart in the original high-dimensional space. So we've got these sort of attractive and repulsive forces pushing and pulling, and we're just going to optimize until we stabilize with respect to that. That all sounds nice, but does it actually work? So here's that algorithm, UMAP, on the MNIST digits data set. So here, MNIST digits is handwritten digits, digitized as 28 by 28 pixel images. And I've color-coded this by which digit that particular image represented. And you can see it's classified all the different digits very nicely into separate groups, but it's also picked up some of the aspects of which digits are similar to each other. So 1 is very different from 0. They're at opposite sides of this diagram. Whereas 4, 7, and 9 are up in the top left there, and 8, 5, and 3 are in the middle. Those sort of triples of digits actually look kind of similar to each other when you handwrite them, especially if you cross your 7s and draw your 4s badly. So you can see how we've actually gained a lot of insight about the structure that's going on here. And this is a 2-dimensional representation of data that was originally 784-dimensional. So it's actually doing a very good job. Here's fashion MNIST, which is sort of a drop-in replacement for MNIST. This time, instead of handwritten digits, it's black and white photographs of fashion items like shirts and shoes and so on. And you can see, again, it's mostly classified the different classes very cleanly, but it's also said that footwear is quite distinct from all the different dresses, shirts, and so on. Yet another example, here's Kazushi MNIST. This is characters in a particular Japanese calligraphy script. And once again, we've got separate classes, all cleanly separated. Some of them, though, are split. There's multiple clumps under a given color. It turns out that if you actually mouse over those and find out what the individual items are, there are surprisingly different ways of drawing a given character, and they do actually make sense to be separated like that. So overall, this is working pretty well in practice. But we can go a little further, and we can try and do something like metric learning. So here's Siamese or triplet networks on fashion MNIST, and the goal here is that on the left, we have a training set of data, and we're going to learn a representation based on the labeling of the data. And then we're going to be able to transform new data into that learned space so that we've learned a metric space that separates the different classes. This is what Siamese and triplet networks are for. They do a great job of this. If we apply UMAP to the same sort of problem, we see that we get much the same quality of results, but the individual clumps associated to the different classes of fashion item are actually well represented in terms of their internal structure as well. Instead of just being a fuzzy blob that we managed to at least separate into the different clumps, we've actually learned more about the metric in terms of the internal structure of each of those blobs. So while all that math at the start sounded very abstract, it actually does a remarkable job of building up a nice, rich dimension reduction technique. But we couldn't do more. So word embeddings. This is still ongoing work, so what I'm going to present here is in some sense preliminary, but I thought I'd try and share it anyway. So the goal of word embeddings is I have a whole bunch of text, and I would like to represent words by vectors so that I can plug these vectors into standard machine learning approaches. But if I'm going to represent a word by a vector, I don't really want a giant high-dimensional one-hot encoded vector that doesn't tell me very much information. I'd like a short vector that has some information about how words relate to each other, so that nearby words, or words that are synonyms for each other, for example, should have vectors that are close together, and so on. So this is where algorithms like word2vec and glove and things like that, fast text, all come in. So can we apply these topological techniques to this sort of approach? So to start, we need to have some way to represent any of this at all. So the underlying hypothesis behind, in fact, all of these techniques that I just mentioned is this distributional hypothesis. And it's really actually just a rephrasing of something called the Yaneda embedding from category theory. So this is my claim that category theory actually explains way more than you think it does. But the essential idea is that, quote, you shall know a word by the company it keeps. In other words, you can understand a word's meaning if you can understand everything about how that word is used. If you know all the words that a word is used with, you, in the end, ultimately understand what that word means. So the goal here is that we're going to represent a word as a multinomial distribution of the words that it co-occurs with in our training text. So in other words, we're going to scan through our training text, and whenever a word gets used, I'm going to look at the words around it, and I'm just going to keep track of how often those words get used around this specific word. And then we can just turn that into a straightforward multinomial distribution, so that in a sense we can say, well, if this central word was the word that was used, these are the probabilities of these other words showing up around it. That's going to be a very large and very, very sparse matrix, because it's going to be the size of your vocabulary by the size of your vocabulary. That's not a great thing to be working with in practice. But we could, in principle, find the manifold on which these words lie. There's some topological structure to language and how words get used. And if we can dig that out of this high-dimensional representation, then maybe we can get some useful word vectors. So the assumptions here that are going to go into this are that uniform distribution assumption, so that we can use those topological techniques we wanted, and that the data is locally connected. The manifold is locally connected. And that's the important one that's going to work for this very high-dimensional data, because this is crazy high-dimensional. It's vocabulary-sized dimensional. So if you have a vocabulary of 200,000 words, you have 200,000 dimensional vectors. And trying to apply something like TSNE or other techniques to that is going to work surprisingly poorly. But here's the thing. The curse of dimensionality is kind of what kills these techniques at this high dimensionality. And the catch here is that distance gets strange in high dimensional spaces. So here's a plot of the distribution of distances to the 20 nearest neighbors of some data that's just sampled from Gaussian. And we're going to look at that in 2 dimensions. That's the blue. It's a very tight distribution, kind of near 0. In 8 dimensions, in the green, it sort of slides up a little bit. By the time we're at 128 dimensions in purple, in general, most of your distances are all in the 12 to 16 range. They're quite large. And as you get higher and higher dimensional, you're just going to get further and further out. The majority of distances are all just large. And so the catch is that, in general, to make sense of these things, you want to normalize all your distances back so they're on a nice, convenient, similar scale to each other. If we do that, this is what we end up with. The 2-dimensional data renormalized back, so we're just dividing by the largest value we see. The 2-dimensional data is still nicely distributed near 0, but now these other higher dimensional distributions get tighter and tighter, because we're normalizing by larger and larger numbers, but the lowest value we see is also very large. And this, in the end, is what gives you one of the effects of the curse of dimensionality, which is that when you normalize your distances back in very high dimensional spaces, almost all distances look approximately the same. because the distribution of distances that you see is this very, 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 very tight distribution where they're all essentially almost exactly the same. But if we apply this local connectivity assumption to very high dimensional data, we find that a strange thing happens. When we apply that local connectivity and then normalize, the distribution looks essentially the same no matter what dimension we're in. So the distribution of distances with this local connectivity assumption applied looks just like the distribution of distances in 2 dimensions. So now we can actually work with ridiculously high dimensional data and understand these distances surprisingly well. So that means that we can actually apply a technique somewhat like UMAP to this data that is 200,000 dimensional and still extract meaningful structure out of it because we're actually still understanding these distances well, even in these ridiculously high dimensional spaces. The last thing that you need to do is work out what the correct metric to use is for multinomial parameter space. And I had some colleagues who worked on that for me, and they just pushed through a whole bunch of statistical geometry. I don't know the details myself. It's kind of fun, but the end result is that you can actually come up with a correct notion of how to define distance between very large multinomial distributions. And when you apply all of that to the problem of word embeddings, you can get something like this. So this is an example embedding of Yelp reviews. Now, we've taken all the words used in a whole bunch of Yelp reviews and embedded them in 2 dimensions. This is not a TSNE or UMAP plot of word-to-vec vectors. This is directly going from that 200,000 dimensional representation straight down to 2 dimensions. These are 2-dimensional word vectors rather than the, say, 100 or 300 dimensions you might get from word-to-vec, and yet they still have a lot of these similarity relations that you would expect to find out of word-to-vec vectors. So in essence, we can build word vectors that are extremely low dimensional. We could do 2, we could do 10 dimensions and capture a lot of this information. Why are we able to go to such low dimensions with a technique like this? Because we're actually understanding the topology and the manifold of this language vocabulary. Word-to-vec, at the end of the day, if you dig into what's actually going on with that technique, or GLOVE, or even fast text, are essentially linear projections. You can't understand complex curved manifolds with those sorts of techniques, and so you can't embed to very low dimensions and get low dimensional word vectors without losing a lot of information. But if you have something that understands the topology of the language, then you can actually get very low dimensional word vectors out and understand a lot about the language without losing much in that projection down to very low dimensions. Okay, so what else could we do with these sorts of crazy topological techniques? Well, how about clustering? So to start with, we need to know what we mean by a cluster, because that's not as well defined as one would necessarily like. So for my purposes, in terms of the sort of work I do, I tend to find that density-based clustering approaches are the ones that make the most sense. So in that sense, a cluster is a connected component of a superlevel set of the probability density function of the underlying and unknown distribution from which the data samples are drawn. It's a long and complicated definition. Let's look at it on an example so we can see what's going on. Here's some data. It's data in 2 dimensions so that we can see what's going on. We can, in principle, imagine that there's some notional probability density function, which this heat map represents, that gives the probability of sampling a point from that region of the space. Ideally, we can turn that probability density function into a set of level sets that sort of demonstrate the different levels of that probability density function. We could pick a given level set and say, what are the connected parts of that level set? Because we've got a whole bunch of distinct little components there, and each of those is going to lasso some data. So each one of those groups of data that's lassoed by this technique is a cluster. So that's the notion of clustering we're talking about, going through essentially this process. The catch is that we don't actually know that probability density function that I started off drawing that made all of that look so straightforward. how do we actually compute that or even approximate it to do anything like that sort of nice process that seemed to pick out the clusters pretty well? Okay, so here's some even more toy data, but it's going to be easier to draw our example on this data set. So the assumption that's going to go into this is that the data is distributed on the manifold according to some probability density function. And in fact, this time we're not going to be pushing for a uniform distribution of the data. We want that probability density function. That's the piece of information we're after. So what we want to do is choose a metric that's going to not only preserve that distribution, but in fact, potentially emphasize it to try and sweep away some of the noise that crops up in data. So if we do that, what we end up with is a whole bunch of local metrics that may be incompatible with each other. But this time around, we're going to do the opposite and try and solve this system of constraints and use limits. But once again, limits of metric spaces, not so easy to work with. But we have this way of translating to a purely topological representation that's still combinatorial, so we can still compute with it. And there, we can compute limits, and everything works out nicely. And what we would get is a probabilistic graph, if you like. It's the one skeleton of this fuzzy simplicial set. And if you stare at this, you can see that what that topological structure is actually capturing is the probability density function. So in some sense, we've captured the topology of the probability density function by just going the other way and emphasizing the distribution rather than smoothing it out and looking for a uniform distribution. But we want the connected components of that. That was kind of the point. We wanted level sets and connected components. But in a purely topological setting, connected components is actually a thing. There's a named thing called pi naught, which is literally just a functor that translates from topological spaces to connected components. And you can compute with that, especially if you're working with this nice finite combinatorial notion of topological spaces. And because we're working with a fuzzy topological space, what we're going to get out is a fuzzy set of connected components. So as long as we exclude some components that are below a given threshold size, they're too small to be considered a cluster. 2 points, that's not a cluster. That's just 2 lonely points by themselves. And prune those out as being too small. We can sort the points according to the component membership of which cluster they belong to when at different membership strengths. And you get essentially something like this, where there's a varying membership strength and the points are sorted in an order. And from there, you can pick out clusters. You can use various techniques. There's information theoretic techniques. There's persistent homology-based techniques. You can just take the leaves of this essentially cluster tree that you would get out. You can see one technique has picked them out here. And what we get out would be that. So at least for this ridiculously toy data set, we have successfully clustered that data, I think, probably according to what your eye imagined was there. But what about more complex data? So how about our original data set? Well, this is the clustering job that approach would turn out there. And again, I feel like this is what your eyes probably saw when you stared at that data, whereas techniques like k-means or other similar related approaches are not going to turn this clustering out for you, because you have oddly shaped clusters, you have noise in the data. It defeats a lot of the standard clustering algorithms, but with this approach, it just falls out incredibly naturally. And in fact, if you're familiar with the HDB scan clustering algorithm, you would know that it manages to cluster the data kind of similar to that. It turns out that you can actually rephrase pretty much all of the HDB scan clustering algorithm entirely in terms of these topological techniques. And it explains how to do that algorithm topologically and makes a few different choices, which ends up with this, which is in fact a more robust and better clustering algorithm than HDB scan. But better still, we have these membership strengths for each individual point. And in a sense, you can interpret those as the probability that the point is in any connected component. So in practice, that's a very meaningful outlier score. So here, the points are colored by that membership strength. The more yellow the point is, heading through greens and yellows, the more likely it is to be in a connected component. And you can see that we have managed to provide a pretty strong picking out of all the outliers here, and we've classified the different clusters according to how outlierly they are. That much looser cluster in the upper left is much less inlying, or it's more outlying than some of the denser clusters elsewhere. So in a sense, by using this technique, we've actually built an anomaly detection algorithm just for free on the side. It comes automatically. We didn't have to compute anything more to do it. We'd already computed all of this. So, in conclusion, topology and category theory actually provide a different language to frame some of these classical unsupervised learning problems, but it's a very powerful language, and these topological techniques can provide surprisingly powerful solutions, at least to unsupervised learning problems. And so, hopefully, I've motivated you to learn some more about them.